I'll start sharing my screen. Just hold on for a second. So I hope you can see my screen. If you have any difficulties, please let me know through chat box. It seems that I can't hear. I can't actually hear the participants. I'm not sure what's going on. So anyway, I'll introduce myself. This being the first class. Yes.
Yes, sir. Your slide is visible.
Is it visible? All right.
Yes, sir. It's visible.
Okay. Any more further issues?
No, sir.
Okay. All right.
You can continue.
All right. So far only you have joined. I hope the others would join in the during the course of this session. So how are you finding the course?
Yes, sir. As I'm just new to this course.
All right. Yeah.
So just now I have started learning.
Okay. So how far have you advanced in the course?
So just now I have started learning week 1, sir.
Week 1. Okay. So is your week 1 assignments on yet?
Department?
Or, I'm sorry?
No, sir. No, sir. Not yet completed. Not yet completed, sir.
All right. So I'll be assisting the faculty who's dealing the course, Dr. Shantakumar, in conducting tutorial sessions. So the purpose of this tutorial session is to assist you to carry out the assignments on your own. So I've tried to make this tutorial session as close as possible to the assignments that you would be doing. So if you can try and understand what is being discussed in these tutorial sessions, I suppose you won't have much difficulties in clearing the assignments in the course. Is that fine?
Okay, sir.
That'll be fine.
Yes, sir. Okay, sir.
So I'll introduce myself. I'm Isaac John. I'm a PhD scholar from IIT Palakkad. So my area of research is basically in robotics. It's related to robotics, and I'll be assisting Dr. Shantakumar in conducting this course, Wheel Mobile Robots. So as you know, this is the first session. And what are the topics that you have gone through? Have you covered all the topics? Have you covered all the topics in week 1?
Yes, it's going on, sir. So I just started watching, sir. As I belong to CSE department,
Yeah.
so yes, sir. Just feeling a little bit difficult to move on, but okay, the lectures are very easy to understand, sir.
All right, yeah. So if you have watched all these lecture series and if you have attended these tutorial sessions, then you won't find any difficulties in solving the assignment. So I suppose you might have already covered all the lectures. Then you'll be able to figure out how to solve these assignments on your own. I could guide you, no problems.
Okay.
Shall we begin?
Okay, sir. Okay.
Okay, all right. So
yes, sir.
Yeah, we'll start with the. If you have any doubts, you can always interrupt me. If anyone is joined in between, they can also interrupt the discussions. And if they are having any difficulties in following, you can always raise your question. All right.
Okay, sir. Sure.
So we'll go to the first question. So the first question is basically a descriptive question. It says the effect on the environment causing the motion of the objects is called. So since you are the only participant, could you answer what could be the correct answer? Effect on the environment causing the motion of the objects.
Causing locomotion, sir.
Are you sure? Because we have a robotic system.
Sir, locomotion is what? It's manipulation, sir.
Okay. Could you decide on one of these options?
Okay, sir. Then.
Yeah, I'll just give you a brief overview. So we have basically
motion of the objects, sir.
Objects around. Yeah.
Yes, so sir. Two robotics.
Yeah.
Yes. One is locomotion, another one is manipulation, sir. So yeah, locomotion is when the object it starts moving around, it's locomotion.
Yeah.
Manipulation is it's fixed at one point and it starts moving the objects around.
objects around. Yeah, now you got it actually. So in terms of, basically there are two robotic systems. You can classify a robotic system roughly in two categories. One is called manipulator, and one is called a locomotion system. So what the manipulator does, as you have correctly explained, the manipulator has one of its link fixed to the ground, and the series of these links are basically actuated using motors or individual actuators. So with the help of these actuators, you would have a controlled motion of all these links, so that the objects within its workspace can be manipulated, can be displaced to some other location as per our requirements. So this process is basically called manipulation. So the effect on the environment. So the effect the manipulator puts, the robotic system puts on the environment, which causes the motion of the objects around, is called manipulation. But the effect causes the motion of the system itself. So the effect in case of a locomotion system, the effect on the environment would be the tractive force exerted by the wheels. So what is the cause of this effect? It would be the motion of the system itself. So that process is called locomotion. So in this context, the correct answer is manipulation, because the effect on the environment causing the motion of the objects around is called manipulation. So is anyone of you having any doubts on this? Are we all? I hope we are all agreeing on this. If anyone is having any issues in this or any difficulties in understanding this, or if the point is not clear, please do let me know. Otherwise, we'll move forward to the next question. All right. So the second question would be the effect on, sorry, this is the correct answer. And question number 2 suggests what are the traditional 3Ds of robotics? So if you take any standard robotics textbooks, you won't see these things anywhere. But when it comes to an industry's point of view, industries would usually delegate automation only in specific tasks. You cannot use automation for every task, because you cannot use automation because the return of investment would not be sufficient enough, good enough, or it won't even break even. The returns from whatever we are investing won't break even compared to the capital we are basically investing. So from in the earlier days, when people started to automate tasks that is being carried out in manufacturing industries, people would normally use automation or robotics for tasks that are, which of them would be correct? Design, detail, or delicate, dull, dirty, or dangerous, dull, discipline, or domestic, dear, dimension, or domestic. Option 5, domestic, domain, deal, dirty, deep, and domestic. Which of them would be the correct answer? Anita says option 2. That is indeed the correct answer. Option 2, because in earlier days, at the beginning of automation, when we started implementing automation on industries, we would do automation for mostly tasks that are dull, dirty, or dangerous. Dull in the sense, I would give an example. In case of assembly lines, where people are employed, after some time it would get tired because they are doing repetitive jobs without any break for a long time. So assembly line jobs are mostly dull, and dirty, like jobs that comes under the dirty class, mostly related to cleaning and sanitization. So an example would be cleaning of manholes. Sometimes it's incredibly dehumanizing, and it's also dirty, basically, whatever they are doing, and it's not a work that a human should do anymore these days. And dangerous, such as operating in nuclear wasteland, areas where nuclear waste is predominant. Employing people wouldn't be the wise choice anymore. or even inspection of heavy structures or tall structures such as bridges and all those things. So we would usually, traditionally, people would use automation for tasks that are dull, dirty, and dangerous. These days, they have added more D such as difficult, because in these days, you would see robotics being used in surgical robots, so in surgeries, which is an incredibly delicate and incredibly difficult task. But the question specific to this question would be traditional 3Ds. So that would mostly correspond to dull, dirty, and dangerous. So I hope that is fine. The reasoning is fine. So yeah, again, to emphasize my point, this view of robotics was mostly from the industrial point of view. So, and again, if you look at the third point, automation is not the answer to everything. It's this is basically an article. So if you can search this upon Google, you will have a very good article regarding why robotics should be employed only on dirty, dull, and dangerous tasks, and why automation is not an answer to everything. It should be mostly employed for dirty, dull, dangerous tasks. So I hope the reasoning is clear, and I hope the participants are not having any conflicts regarding this question. If you are having any difficulties or if you are having any issues, please let me know. You can either comment on the chat box, or you can unmute yourself and feel free to let me know. All right. So moving on to the third question. So theoretically, conventional wheels can move in, which is the correct option? Only in lateral direction, only in longitudinal direction, both lateral and longitudinal direction, no specific directions, only in vertical direction, all three directions. So what could be the answer? So if you consider a traditional wheel, so a traditional wheel would be actuated using motors. So if this is the wheel axis, you would basically actuate the wheel using motors that is aligned in parallel to this shaft. And what are these lateral and longitudinal direction? So longitudinal direction, we'll start with the lateral direction. Lateral would be the direction that is parallel to the axis of the wheel hub. So this is lateral direction. And the in-plane perpendicular direction perpendicular to this would be longitudinal. And you might have come across wheel configurations that might have passive rollers in the introductory lectures. But here we are only dealing with, notice the keyword, we are only dealing with conventional wheels. It doesn't have any passive rollers. We are only using motors to actuate the wheels along its own axis. So theoretically, in case of conventional wheels, you will have infinite resistance, like how we model these wheels in mathematical models. We'll have infinite resistance in lateral direction. So if we are having a wheel, it can't move sideways. It can only move along its longitudinal direction. So in this regard, what would be the logical answer? The correct answer would be the wheels can only move along its longitudinal direction. Note this point. This could be answered in your assignments or in further quizzes, like how if you are modeling the conventional wheels, we'll model as if conventional wheels have infinite resistance in lateral direction. It won't slip. It can only roll along its longitudinal direction. So I hope this reasoning is good enough. I hope this is clear enough. So moving on to the next question. For a land-based mobile robots and wheel surface vehicles, the degree of freedom is. So can any of the participants answer this question? Okay, Sanju says 3. What about Murali? Anita? Okay, Anita also says 3. And the answer indeed is 3. So what is the definition of degrees of freedom? So degree of freedom would be, the brief definition of degree of freedom would be, we'll write D of in shorthand, is basically number of variables required to fully So the degrees of freedom in this context would be the number of variables required to fully define the system's configuration. So land-based robots. So as you can see, land-based robots can only move in land. It can only move in a plane. It cannot go up and down. And in case of water surface vehicles, it says water surface vehicles. Notice the keyword. It cannot go underwater. It can only sustain, it can only operate in the water surface levels. So this how many degrees of freedom does a planar robot have? Planar robot require? How many variables are required to fully define a system? So if you consider this slide or this screen as a plane, so if I'm fixing this as the origin of this plane, and if this is the chassis of a robot, and this is a locally attached frame, small x and y, and this is the origin attached to the ground, and this is the local frame, and this is the inertial frame. So how many degrees of freedom would you require? You would require 2 degrees of freedom to 2 variables to define the position, two position coordinates to define this frame's location. You would need to define what is this x distance and what is this x distance and what is this y distance. Apart from that, you would also need one angle to specify its orientation also. So the position alone won't suffice. You would also need one more variable, an angular displacement about an z-axis that is orthogonal, that is perpendicular to this plane, to fully define the vehicle's configuration. So in this sense, you would require 3 degrees of freedom to fully specify a robot's configuration. I hope that is clear. All right. So the answer is indeed 3 degrees of freedom. You would require 3 degrees of freedom for wheeled mobile robots and water surface vehicles. So how many degrees of freedom does a aerial robot has? Can anyone reply to that question? In case of an aerial robot, how many degrees of freedom does it require? Sanju says 6. What about others? Anita and Murali. You can also speak up, no problems, if that is not a concern. Okay, Murali says 6. Anita hasn't responded yet. So the answer is indeed 6. So in case of an aerial vehicle, you would require 3 position coordinates to locate its position of the frame that is attached to the body. And also you would require 3 orientation variables to specify its orientation in space. So the answer is indeed 6 for an aerial vehicle. All right. So I take it that it is clear for all the participants. Moving on to the next question. So degree of mobility of a mobile wheeled robot. Degree of mobility of a wheeled mobile robot is option 1, the degree of freedom that the robot manipulates directly through the wheel velocity. Option 2, a degree of freedom that indirectly manipulates by changing the steering configuration and moving. Option 3, the total number of controllable inputs is always 3 for a wheeled mobile robot and water surface vehicles. Is the sum of degree of freedom and steerability. And option 6 is the sum of degree of maneuverability and steerability. So what could be the correct answer? So it is very difficult, easy to get confused with these terms. Degrees of freedom, degree of mobility, degree of steerability, and degree of maneuverability. So in this course, you will be coming across all these 4 terms. So it could be very easy to get confused with all these 4 terms. Degree of freedom we have already discussed in the last question. So we have all agreed upon the fact that it is the minimum number of variables to fully define or describe the configuration of a system. So in this question, they have specifically asked degree of mobility. I suppose you might have come across the term called degree of mobility. So in this case, what is the correct answer? What is the correct answer? So can any of you contribute? Can any of you say the answer? Sanju, Murali? All right. So I'll go forward. So yeah, degree of mobility essentially means, as per the definition that is being followed in our lectures, typically motors are used for directly manipulating the wheel's velocity. If we attach a motor on the wheel hub, we can directly manipulate the wheel velocity using one motor. And the other way of using primary purpose of using motors would be to manipulate the steering angle. So if the wheel is connected to a shaft or onto the chassis, and if we attach a motor, we can basically manipulate the steering angle as well. So the term mobility basically corresponds. It basically corresponds to the degree of freedom that the robot directly manipulates directly through the wheel velocity. So in case of a 4-wheeled robot, I'll give you a few examples to understand this point. So in the case of a robot with 4 wheels, and each of these 4 wheels have its own motors. So we are directly manipulating the velocity of each of these 4 wheels, wheel 1, wheel 2, wheel 3, wheel 4, with 4 different motors. So in this case, the mobility would be 4, because we are using 4 motors to manipulate the velocities, the wheel velocity of all these individual wheels. Another example would be if we are using a single motor to manipulate the wheel velocity of 2 wheels. We can connect 2 wheels through a common axle. And again, if you are using a single motor, a common motor, and the motion is transmitted to the 2 rear wheels. These are the front wheels. These are the rear wheels. Then what would be the mobility? We are using a single motor or a single degree of freedom to manipulate the 2 wheels of the front axle, and a single motor to manipulate the wheel velocity of the 2 rear wheels as well. So in this case, the mobility would be 2. So I hope the point is clear. I have given 2 examples. So mobility would be the definition of mobility. Degree of mobility would be the degree of freedom that the robot manipulates directly through the wheel velocity. So that is the correct option. And the degree of freedom that indirectly manipulates by changing the steering configuration. This is the definition of steerability. We are not directly manipulating the wheel's velocity. We are indirectly manipulating the wheel velocity by using a separate axis, that is manipulating the steering axis. So that is called the degree of steerability. And the first definition, we are having direct control over the wheel's velocity, that is degree of mobility. And the total number of control inputs, what could that be? This is basically what we call maneuverability. Maneuverability. Total number of control inputs would be maneuverability, as you might have seen in the lectures. Maneuverability is simply the sum of degree of maneuverability is simply a sum of degree of mobility and degree of steerability. So if someone asks what is the total number of controllable inputs, they basically mean maneuverability. And the other three options are basically, it's not relevant to our question. It's always 3 4-wheel mobile robots and water surface vehicles. That corresponds to the degree of freedom that we have discussed in the previous question. Is the sum of degree of freedom and steerability. It's not the right answer, and is the sum of maneuverability and steerability. Again, that is not the right answer. The correct equation for maneuverability is this one. So I hope the reasoning is good enough. Mobility would be the degree of freedom that the robot directly manipulates through the wheel velocity. That is what we call mobility.
Can I ask a question?
Yeah, please.
Can you go to the previous slide, please?
This one?
Yeah.
All
so,
right.
You mentioned that the degree of maneuverability is the sum of degree of mobility plus degree of steerability.
Yes.
So in the example, in the second example, which you mentioned, the way that we have 4 wheels with 2 wheels being connected to each motor.
Yeah, let me recreate that example. Yeah.
So in that, we have 2 motors controlling, each one controlling 2 wheels.
Yes.
So we have degree of mobility being 2 there.
Yeah.
So does it mean that degree of freedom for maneuverability is 2 here?
I'm sorry.
So this is, see, degree of freedom for mobility is 2.
Yeah.
And degree of freedom for steerability is 0, I guess.
Degree of steerability is 0 because we haven't specified any axis or any inputs for manipulating the steerability of this mechanism. Yes.
Yes, 0. So
yes.
So that means that degree of freedom for maneuverability is 2.
Degree of maneuverability is 2. Yes.
So yes. Even though we can't steer the robot, it still has this maneuverability option.
It still has maneuverability, but this is a made up case. This is basically redundant because in order to achieve the motion that this robot is trying to achieve, you don't need 2 axles, right? If you make this passive, it will still execute the same motion, right? It can only go straight. It doesn't matter if you have one more motor, one more identical configuration at the rear. It can only still go in the straight line, right?
Yeah, it does. It goes in straight line. But what I'm trying to clarify is that this maneuverability. Yeah. So even though this doesn't seem to turn, it still has this maneuverability defined as 2.
No, steerability is 0 actually. Steerability is still 0. Yeah.
So even though it can't steer you can't steer the robot. Yeah. You still have the maneuverability being 2.
Maneuverability is still 2. Yes, exactly. But the thing is that I only made this example to make the point of mobility, degree of mobility clear. But fine. This configuration doesn't exist, shouldn't exist actually, because this is a made-up configuration. This shouldn't exist because this is basically a useless configuration, right? It can only move back and forth. It doesn't steer or anything. But due to the fact that we have incorporated 2 motors, while specifying it, technically the maneuverability is 2, but we shouldn't even be discussing about this configuration because it has no use or anything. I will discuss more realistic configurations in the upcoming questions. So If the concept is still not clear, you can again interfere or intervene.
No, concept is clear. Just that I got because the example you showed.
I agree with your point. Just it's only due to the fact. See, the degree of maneuverability essentially means the number of controllable inputs. So due to the fact that we have defined two motors, we have to control them. That's the only requirement. So if we simply eliminate this axle, and let these two wheels rotate on its own axis freely, then the degree of maneuverability would be 1. So if you want a robot that would only want to move in a straight line, only this configuration is sufficient. Only this axle is sufficient. You wouldn't need a secondary axis like this, right? You wouldn't need. So in this regard, degree of maneuverability would be still 1. Degree of mobility and degree of maneuverability would be still 1. I only added a second axle to demonstrate what effect it would have on this degree of mobility. All right, so we'll come with more realistic examples in the upcoming questions. So maybe we can see whether the concept is clear or not. Your concept is still understand. I understand that you got the point, but regarding this example, it was only made up just to discuss the degree of mobility.
Just for clarifying the definitions part, you put in this example.
Sorry.
Just for clarifying the definitions of these 3 concepts.
All right.
In this example.
All right. Yeah.
So before proceeding further, can I just take one standard example of a robot with the 2 driving wheels being driven independently by 2 motors and having 4 caster wheels? If we can just clarify these 3 concepts, and then we can proceed further.
All right. So I hope this is what you meant. We'll have 4 caster wheels at the corners. And 2 driving wheels and steerable wheels. Like these wheels are drivable and steerable, right?
Driven by independent motors.
Driven by independent motors and steered by independent motors also, right?
Yes.
All right. So in this case, how many degrees of freedom would you manipulate directly through wheel velocity?
So 2 controllable inputs, right?
Yeah,
so
we give 2 controllable inputs to these motors, to these wheels independently.
Yes.
So degree of mobility would be, what would be the degree of mobility in this case? It would be 2, right? Because you directly manipulate the wheel's velocity through two independent motors. Just the wheel velocities, as of this moment, just forget about the steerability. But for the mobility part, the definition of the mobility, as per this question, the definition of the mobility says the degree of freedom that the robot manipulates directly through the wheel velocity.
So that means that if the 2 motors run at the same speed, the robot will travel in a straight line.
Yeah.
And if they run at the differential speeds, then it can have a curved path.
It can turn. Yes.
So in that sense, you are saying degree of mobility is 2.
Degree of mobility is 2. Yeah. And what would be the degree of steerability? If we are having 2 independent motors to control the steering of this system, you would have 2 degrees of steerability as well.
So the thing is, we are steering the robot with 2 motors, right? Is that the reason?
I'm sorry?
Why is it 2?
If you want to control independently the wheels separately, axis of the wheels, because you can see in the upcoming sessions, probably from week 2 regarding generalized wheel kinematic model, you would require one of these wheels to be aligned in this configuration and the other in some other configuration, so that it can basically rotate about its own axis. Can you see what I'm getting?
Yes, I do.
See, if this is X, this is Y, and the horizontal axis is Z. So if you want the robot to rotate about its own axis, you would require independent steering of both of these wheels.
Yes, independent steerings, but The thing is, in the first picture you put in the two motors, if I just manipulate the velocity of these two motors in a differential sense, then it will also rotate, right?
It will also rotate. Yeah, exactly. In one direction, in one direction. Yeah, like this, right? It can still rotate. Yes, yes.
So in that sense, well, I'm thinking the degree of stability should be 1 in that case, right, or 2?
Okay, if you are controlling the steering of the board, both of these wheels are as dependent. If both of these are dependent, then the steerability would still be 1. But if you are independently controlling the steerability of these two wheels, then this thing would be 2. I think I cannot recall the exact reason why we need 2 independent steering, but I hope in the upcoming lectures, upcoming weeks, you would find a case where you would require different steering angles. I guess different steering angles for both of these wheels.
Let's proceed.
Yeah, maybe we can discuss that in the next week's lectures if you have if we have come across. So if you require 2 independent steerable axes, then degree of steerability would be 2. If that case is not required, I cannot recall for whatever reason. If the steering of the wheels, both of these wheels are controlled using 1 motors, then the degree of steerability would be 2, and degree of maneuverability would be sum of mobility and steerability. That would be 3. But in this case, if you are independently controlling both of these motors, then we would require the degree of steerability as 2.
And just to add what you said, I mean, I can think of a case where you might need, I mean, there is a possibility of having 2 steering options. For example,
all right.
In the previous diagram which you mentioned about 2 motors driving 2 wheels.
Yeah.
So if I have put in the steering mechanisms differently for the top wheels and bottom wheels, then you can still have a well-defined motion, but with 2 steering inputs.
With 2 steering inputs, yes.
So for front axis 1 steering and the bottom axis another steering.
Exactly. Exactly the right point. If you want the robot to rotate in a circular trajectory or something like that, I suppose differential action would still suffice, right?
Yeah, differential suffice, but you're saying that there might be a case where you need 2 steerable options. 2 independent steerable options. So if you have 2 independent axes running front and back, then you can steer them independently and make a well-defined path.
Okay. All right. Hopefully, we'll come across such examples in the next week lectures.
Sure.
All right. If you maybe if you can raise this question, I can have an informed look on my own, and I can get back to you. If you raise this question in the discussion forum, I can look on my own and I can get back to you.
Well,
on the answer this week itself. Next week, anyway, I'll be going through the tutorial questions, and we'll be discussing that anyway. Because wheel configurations and all those things we'll be discussing in week 2. If you would like to answer, you can raise it in the. If you would like to have more clarity in this, you can raise it in the discussion forum. I will be happy to answer. So as of now, I don't know, for whatever reason I can't recall of that example where you would require. But whatever you said is correct, actually.
No, you are right. Let's go. Thank you. Let's go.
Okay. All right. Thank you. So I hope you are all fine with the reasoning for this answer. The degree of mobility corresponds to the degree of freedom the robot directly manipulates through the wheel velocity. All right. So moving on to question 6. Legged locomotion requires lower or lesser degrees of freedom and therefore is of lesser complexity than wheel locomotion. So I suppose the answer is quite straightforward, right? The answer is obviously false. I hope all of you can agree with this without much reasoning. See, in the case of a leg locomotion, you would require, at the minimum, you would have a hip joint, a knee joint, and an ankle joint at the minimum. And you will have multiple bodies as well. So in case of a biped robot, how many actuators would you require? You would require 6 actuators for a biped robot. And as the number of legs increases in case of an insect-like robot or even a 8-legged robot, you would require more links and hence more actuators. Whereas in the case of wheeled robots, if you are having 3 wheels, you can directly manipulate the wheels velocity using motors. If you are having 4 wheels, you would probably require some suspension without any actuation. The suspension can be managed without any actuation. So obviously, the number of bodies and the number of degrees of freedom to actuate each of these bodies would be comparatively less for wheel locomotion as compared with the legged locomotion. So in this regard, I hope we can unanimously agree that legged locomotion is far more complex and requires more degrees of freedom than wheeled locomotion. So in this regard, the correct answer is false. So I hope everyone agrees with this. Yeah, the correct answer is indeed false. If you have any conflict of opinion, please let me know. Otherwise, we'll move on to question number 7. Again, it's a true or false questions. So please keep in mind that this would be the exact similar pattern that we would be following for the assignments as well. So the assignments consist of multiple choice questions, be it fill in the blanks, you'll have multiple choice questions. You'll also have true or false questions. And occasionally you will also have match the following kind of questions. Again, you will be provided with multiple choice questions. So these are the exact similar pattern that we would be following for setting up the assignments also. So if you have clear understanding in this tutorial sessions, you would have no issues in clearing the assignments in with good grades. All right. So moving on to the question. For a given velocity input commands, finding the derivative of generalized coordinates, or in other words, finding the system's motion is known as inverse differential kinematics. Is this true or false? Murali, can you answer this? Murali says it's false. Sanju, Vaibhav, Anita, do you have a difference of opinion? So, okay, so I'll go with the reasoning. So differential kinematics deals with the mapping between the velocity input commands and the velocity that is expressed with respect to the fixed frame. So eta dot is velocity of the robot expressed with respect to inertial frame. And these are velocities. But by velocities, I generally mean velocities. The final term is an angular velocity. So it has 2 linear velocity components for the first 2 elements, and the final element is an angular velocity components. Velocities expressed in bodies in the robot's local frame. And the Jacobian basically maps the velocities expressed in the body frame with respect to the inertial frame. So X and Y, let this be the inertial frame. And if you have a robot, you will have a local frame attached to this robot itself. And the Jacobian maps the 2 velocity configurations. So there are 2 schemes of differential kinematics, as you might have been aware of. Forward differential kinematics and inverse differential kinematics. So in forward differential kinematics, you would be giving the velocities in wheels frame as inputs, and you would find output in terms of the reference frame, the inertial reference frame, using this relation. So forward differential kinematics would be given psi, or given the psi vector in terms of body frame coordinates, find eta using eta dot equal to j of psi zeta. This is forward differential kinematics. And in terms of inverse differential kinematics, it's basically the inverse problem. You would be given a desired coordinates of velocities with respect to the body fix in terms of the robot's inertial frame, given desired velocities in terms of inertial frame, find theta using theta would be j of psi inverse theta dot. This is inverse differential kinematics. So in this regard, what would be the correct answer? Murali has already said false. So I hope all of you can agree with false. No further reasoning would be sufficient, I guess, in this regard. All right. If anyone of you have any questions or any conflict of opinion, please let me know. Otherwise, we'll move to the next question. So the answer is yeah.
Is that just a clarification?
Yeah.
So what is this UVR actually represent in practice?
UVR basically represents the velocities with respect to the body's frame. Body's frame changes instantaneously. So what are these velocities represented with respect to the frame?
Yeah, it's
frame attached to
with respect to the frame, but what velocities are these? I mean, what component velocities are these?
U basically means the component along the local x-axis. The local x-axis, and V basically means the velocity component along the local y-axis, and R is the angular velocity that is along the z-axis. That would be orthogonal to the plane.
Are you talking about the velocity of the robot or velocity of the wheels? What?
Velocity of the robot's chassis. Wheels velocity we are not discussing as of now.
So we're talking about the velocity of the robot with respect to its local coordinates.
Its local frame, yeah. So if it were a two-wheeled robot, if the robot had two wheels, you would give the velocity in terms of omega-1 and omega-2, this being the first wheel and this being the second wheel. And due to this, you will have to find the mapping between this U, V, R. You will have some configuration metrics, and you will have to find the mapping between the local velocities, U, V, R, and the angular velocities of this wheel. This you would see in the upcoming weeks. You would have to find what this configuration metrics would be. It will depend on the configuration of the robot. So this you will see in the upcoming week. But as of now, UVR is the velocity of the robot expressed, instantaneous velocity of the robot expressed about its own local frame of reference. And in upcoming week, you will find a mapping between UVR and omega-1 and omega-2. If the robot has four wheels, you will have four omegas. So further transformation you would see in upcoming weeks.
Thank you.
Okay, thank you. Okay, question number 8. So it says the velocity, the vector of input velocity command of a land-based mobile robot is given as 100. So the zeta, the local velocities with respect to its local frame of reference is given as 100. And the mobile robot body is oriented 90 degrees with respect to the base frame. It doesn't say clockwise or counterclockwise. I think that is a mistake from the question's point of view. We'll anyway consider it as counterclockwise. All right, so if this is the inertial frame of reference or the ground fixed frame of reference, if we consider the sense of rotation as counterclockwise, 90-degree orientation would mean x-axis would be vertically up, y-axis would be in the negative x-axis of the local frame. If that is the case, then what would be this Jacobian matrix? The general form of the Jacobian matrix was cos psi minus sin psi, cos psi, 0, 0, 0, 0, 1. So since a mobile robot can only rotate about its vertical axis, it cannot have any other rotation about any other axis. This would be the general form of the rotation matrix or the Jacobian matrix. So with regards to 90-degree counterclockwise rotation, what would be the Jacobian matrix? The values would be, if you substitute the value of 90 degrees plus 90 degrees into this Jacobian matrix, it would be 0, minus 1, 0, 1, 0, 0, and 0, 0, 1. And you are also given zeta. You are required to find out eta dot. So as per the forward differential kinematics, what is eta dot? Eta dot would be j of psi into zeta. So if you directly apply that formulation, what would be the value of zeta? This would be, if you do the matrix multiplication, this would be 0, 1, 0. And the answer corresponding to the right answer is option number 5, 1, 2, 3, 4, 5. This would be the correct answer. So this is basically a forward differential kinematics problem. We are only applying that formula, forward differential kinematics formula, to find out the velocities of the generalized generalized coordinates with respect to the inertial frame of reference. So I hope this is clear. If you guys don't have any further questions, we'll move on to the next question. It is indeed option 5. Yes. Okay, so again, the question regarding maneuverability and degrees of freedom. For a conventional car or a van, considering only ground land-based systems, the degree of freedom is dash and the degree of maneuverability is dash. What would be the answer? Murali, can you give out an answer? Murali and Sanju? I hope I am audible. So in case of a conventional car or a van, if we consider it the car to be a front wheel drive, you will have a engine or a motor, a prime mover that is that commonly connects the two front wheels, and it will also have a steering linkage, and the rear wheels are basically passively rotating about their own hubs. So what is the degree of freedom of, the first question is the degree of freedom of a car. What is the answer? Okay, both of you have answered 3 and 2. Degree of freedom is number of independent variables required to identify the configuration. So as you can see, if you are having a local reference and if you are having a car, the car basically can assume any position and it can assume any orientation. It doesn't matter. We can, through multiple reverses and multiple point of turning, we can actually realize any position and any orientation. So in that regard, we require 3 degrees of freedom to fully realize all these configurations, 2 positions as well as 1 orientation. We would require 3 such inputs. And in the case of maneuverability, what is maneuverability? As I have explained earlier, maneuverability is the sum of degree of mobility plus degree of steerability. So in this regard, degree of mobility is 1 because you are only having 1 input that directly manipulates the wheel velocity. A single engine, the power or the motion of a single engine is transmitted to both of these front wheels using this axle, front axle. And degree of steerability, we are using the steering linkage mechanism to control the steering of the front wheels, again using 1 input. So in this regard, the degree of maneuverability is 2. 1 plus 1 is basically 2. So the answer is 3 and 2. Both of you have rightly responded that. All right, it's 3 and 2. Okay, moving on to the 10th question. For a mechanism wheel drive mobile robot, the degree of mobility is dash and degree of steerability is dash. So can you both respond to this answer? Murali and Sanju. I'll draw the mechanism wheel configuration. Mechanism wheel basically has 4 wheels, and each of these wheels would have 4 passive rollers. And each of these motors, each of these wheels would have its own independent motors. Each of these wheels would have independent motors. So what is the degree of maneuverability, degree of mobility and degree of steerability of this mechanism? Sanju says 4 and 0. What about Murali? Murali says 4 and 4. All right. I think, okay. The correct answer is 4 and 0. I suppose Sanju got it right. Murali, do you have any concerns regarding this? You can speak up.
No, I think what Sanju got is right. Yes.
Yeah, because you would use the 4 motors to directly manipulate the wheel velocities. You are not having any further motors or further any inputs to control its steering.
Yeah, I mean, it's possible to control the 4 independently because 4 motors, but ultimately the robot has to move in one direction. Yes.
Robot can move in other directions also. Robot can move laterally just like this. It can move like this. It can even rotate about its own axis. It can move. It's a holonomic robot. It can move whatever way it wants actually.
Yeah, well, you can move whatever it wants, but the 4 motors have to coordinate to move the robot. 4
motors would have to coordinate. Exactly. Correct.
That's where the
yeah, you would see the example. So you in the further upcoming weeks, you would, if you want to move laterally up and down, you would see what all motors need to be actuated in what all directions. So in the upcoming week, you will discuss. You will see how all these what these combinations should. If you want to move laterally, you have to actuate all the wheels synchronously in the same direction. And if you want to move in counterclockwise direction, you would rotate the inner wheels in one direction, and your outer wheels would have more velocity than the inner wheels if you want to rotate in counterclockwise direction. Similar, like the combinations would be discussed in the next week. So I hope the reasoning for the answer is correct. 4 mobility and the steerability is 0. Okay. Again, a similar question in case of an omni-wheel drive mobile robot. So I'll draw the configuration. The omni wheels would have 3 wheels. And each of these wheels have a perpendicularly aligned passive rollers. And each of these wheels will have, again, its own independent motors. So the degree of mobility would be 3 in this case, and degree of steerability is 0. I hope it's exactly similar to the previous case. You are not indirectly manipulating anything with the steering. You're not indirectly manipulating the steering configuration. You are only directly manipulating the wheel velocity using independent motors. So in this regard, it would be 3 and 0. All right. Okay, so 12th question. We only have 13 questions, so bear with me. I hope I haven't taken too much of your time. Question 12 says, dash of a motion system is the minimum number of variables to describe the system. So we have discussed this concept n number of times in this session alone. So the correct answer would be degree of freedom, a minimum number of variables to describe the system's configuration. That would be the degree of freedom of the system. And the final problem is a numerical problem. The vector of time derivatives of generalized coordinates of the land-based robot is given as eta dot 5 to 1. So eta dot is given as 5 to 1. Generalized coordinates of the land-based robot is given. And the mobile robot is oriented 30 degrees with respect to the base frame. Again, the sense of orientation is not given in the question. It's again a mistake from the question, actually. Mistake in the question. So we would again take counterclockwise. So mostly if the sense of rotation is not given, just assume that even if it is the mistake from the question side, you just assume that the sense of orientation is counterclockwise with respect to the fixed frame. In this case, what will be the vector of input velocity command? So this is a case of inverse differential kinematics. Earlier we have discussed forward differential kinematics. We are given the orientation of the mobile frame with respect to fixed frame as 30 degrees. So what would be the Jacobian? Jacobian would be cos 30 minus sin 30, sin 30, cos 30, 0, 0, 1, 0, 0. And you are required to find what is the vector of input velocity, that is zeta. So as per the differential kinematics, the forward differential kinematics equation would be eta dot would be j of psi into zeta. You are required to find zeta. So what would be zeta? Zeta would be j of psi inverse eta dot. So in this case, what would be j of psi inverse? So it should be clear that j of psi is an orthogonal matrix. Orthogonal matrix. So orthogonal matrix, what would be the inverse of an orthogonal matrix? It would be its transpose. So j of psi inverse is basically j of psi transpose, since j of psi is an orthogonal matrix. So if you do the matrix multiplication, cos 30 minus sin 30, 0, sin 30, cos 30, 0, 0, 0, 1, 5 to 1. If you do the matrix multiplication, you will get the vector of zeta, which in this case would be option number 4. It's only a matter of matrix multiplication. I hope the procedure is straightforward. You should be aware that what is given and what you are supposed to find out. Earlier, in the earlier case, it was a problem of forward differential kinematics. We were given zeta and we were asked to find psi. In this case, it is inverse differential kinematics. You were given eta and you are required to find psi. And we are also we have to use the correct equation. We have to find the inverse of the Jacobian matrix. So in this case, the inverse of the Jacobian matrix is transpose only, because the Jacobian matrix is an orthogonal matrix. So the answer is indeed option 4. And yeah, that would be the end of the questions, discussions for this session. If any of you have any more further doubts regarding week 1 lectures, feel free, please let me know. We can try to solve it now itself. Murali as well as Sanju, do you have any more questions, any more queries regarding week 1 content? All right. Sanju, do you have any more? Okay, sorry, Sanju is also fine. So this would be the pattern that you can expect for the assignments. Have you? I hope you haven't tried the assignments, or I'm not sure whether the assignment one is open or not. But For week 1, this would be, you could expect a similar pattern for assignments. Similar amount of patterns. So if you're thorough with whatever is being solved in this tutorial, you will find no difficulties in solving questions regarding assignment 1. If you have any more further issues to be clarified, you can do it. Do it now. Otherwise, you can leave if you don't have any more things to discuss any further. Yeah. I'll keep the session open until 5 p.m. So anyone can join. If you have any doubts, I am happy to discuss. If you want to revisit any of these questions, it's still fine. If you want to revisit any of these questions or any of these previously discussed questions, it's still fine. The contents of these lectures will be uploaded. You can revisit these lectures anytime you wish also. Okay, Murali, thank you. Thank you for your time. Bye-bye. I hope I will see you in the next upcoming weeks also. Yeah, same to you, Sanju. Thank you. I hope I'll see you in next week also. Thank you.